السلام عليكم ورحمة الله.
وعليكم السلام ورحمة الله.
عليكم السلام ورحمة الله.
السلام ورحمة الله.
Well, so Bismillah, alhamdulillah, salatu wassalam, rasulullah. Today, inshallah, we'll continue automatic generation control. And as we discussed earlier, the major objective of this study is to keep the transformer, the frequency at 60 hertz. So we need to keep the frequency constant at 60 hertz. So we need to adjust the control loop of the generator. As we mentioned here, we have this generator and we have two control loops. One control loop through the excitation, so this will adjust the voltage, and the other control loop through the governor, which controls the steam flow or the mechanical power input. So we need to adjust the mechanical power input to adjust the speed, and the speed is proportional to the frequency. So we control the frequency by adjusting the mechanical power input to the generator. So we are targeting this loop. In this study, we are targeting this loop. So since it is a control system, so we need to model it. We need to model each component. We need to model the generator. We need to model the turbine. We need to model the valve. We need to model also the governor. So we need to develop the block diagram of all the system, so we can study if we have a step input here in electrical power or load. If we have a step change in the load, what is the impact on the frequency and how we can control the frequency to bring it back to 60 hertz. So what we will start today, inshallah, as we mentioned earlier, we start developing the model of the system. So this is the main or like a core equation of motion or equation of rotation. This is the second law of Newton, where you have here the net force equal to the mass times the acceleration. So if you have this as rotating or rotation, not linear motion, so angular rotation, in this case we have the inertia multiplied by the acceleration, and the acceleration is d omega angular speed by dt, or d square delta angular displacement by dt square. So this is the inertia of the system, and this is the acceleration, and this is the net force or net torque or net power. You have the input is B mechanical and the output is B electrical from the generator. So based on this equation, we can model the generator. If you take the Laplace transform for both sides, then you have Bm of S minus P electrical of S equal to Ms omega of S. So you can develop the block diagram of the generator. So this is the definition of omega alpha and delta. B net force or net acceleration power, accelerating power, B mechanical minus B electrical, and then with the angular momentum on the inertia of the machine. So if you take this Laplace transform for this, but of course when we develop the block diagram, so we are talking about linear system, and in linear system we use like a small increment in order to develop the linear system. يعني we are linearizing the system around the operating point. يعني assume that this is the system and we need to linearize. This is the operating point, so we can linearize around this operating point. يعني we can assume and we have very small displacement in power, very small displacement in speed and so on. يعني you can convert this as delta B mechanical minus delta B electrical equal to M d incremental change in omega by dt. If you take Laplace transform, so this is delta B mechanical of S minus delta B electrical of S equal to ms delta omega of S. So you can of course say delta omega of S equal to 1 over ms multiplied by delta B mechanical minus delta B electrical. And you can represent this equation by very simple block diagram. You can have here 1 over ms, and the input here is delta B mechanical minus delta B electrical. So this is minus and this is a plus. So, and you have here the output is delta omega. You can represent this by block diagram as such. It's very simple, straightforward. So you can do this, and you can represent the generator now by this block diagram. So 1 over ms, and the input is B mechanical minus B electrical, and output is delta omega. We will go to delta B electrical, and we divide it to two divisions. One, we can say non-frequency sensitive load change. Yani loads doesn't change with the frequency. So you can have this delta B electrical as delta BL plus frequency sensitive load change. Yani you can have some loads in your system which is sensitive to the frequency. As we mentioned, probably we still remember, we mentioned if you have induction motor and you change the speed of the induction motor, and this induction motor drive pump or fan or any centrifugal load, in this case the power is proportional to n cube. So and the n, definitely n of the synchronous machine of the induction motor depends on the frequency, and ns equal to 120 f over b. So if you have a change in frequency, you have a change in power. So this is some kind of the load that depends on the frequency. So you can divide the delta B electrical in the block diagram here, in the previous block diagram, you can divide it to two terms. One is constant and the other depends on delta omega. So multiplied by here by d. So we can add it as such. We can say this is delta B electrical, which is delta BL plus d times delta omega. And definitely based on your experience in block diagram reduction, we can reduce this by g over 1 plus gh. This is the feed forward transfer function, and this is the feedback. So we can have g over 1 plus gh. So we can end up with this model or this block diagram. So this is delta B mechanical, and this is the delta BL constant power or constant load, doesn't depend on the frequency, and this is the generator now representation. So we will go further and see this delta B mechanical comes from where? Delta B mechanical. This is the load, okay, and this is the generator, and the output is a frequency 2 by f or 2 by times delta f. So delta B mechanical comes from where?
From the turbine.
From the turbine. So we need to simulate also the turbine in the same method, same manner here. We need to have a block diagram which represents the turbine. Usually we use first order, blocks, as you can see here. So this is the physical structure of the power plant. You have here high pressure steam comes from the boiler, and this high pressure steam goes to this called high pressure turbine, and you may collect this steam at the end, and you send it back to the boiler for reheating. And from the reheating, you can bring the steam back to, let us say, intermediate section of the turbine. And the output of this, the steam here at this, goes to the low pressure section of the turbine. And you can have two sections also in the low pressure part, section A and section B. And at the end, you collect the steam here and you condense it and you send it back to the boiler. Okay. And the output power here is a B mechanical, which going to the as input to the generator. So what we need to do now is to simulate this process of the generator, and you can easily assume it as first order block 1 over ST, and this is the charging time where you collect the steam, and then to get the output there is a time delay between the input of the steam and having the mechanical power output. So this represented by the time constant here. So this is called the charging time, or you can say turbine time. Maybe in some literature you can have it as TT, turbine time constant. Okay, so this is the turbine time constant. So you have here valve. So this is the valve representation. This is the power comes from the valve, or the steam comes from the valve, and this is the output mechanical power from the turbine, and this is the representation of the turbine. So this is we can combine now. We can extend this to having this summing point here, where we have here delta BL, and this is minus, and we have here the generator 1 over 1 plus MS D plus MS. Okay, 1 over D plus MS, and this is delta omega. So we can start integrating the components, the generator, turbine, and later we will see the valve power here, and we will see the governor which controls the steam here. We have a governor. We need also to We need also to simulate the governor and so on. So we are building the blocks of all the components of the system. Combine the prime mover or the turbine with the generator model, you end up with this block diagram, and we will definitely go further to see what is the delta B valve and how to build the model. Do you have any questions so far?
Doctor?
Yes, please.
Again, TH represent.
When you have any device, حتى even measuring device, any device, you have any device here. When you give it input, do you think you have instantaneously output, or there is some time delay? This is the input. What do you think the output of the system, of the device, not necessarily turbine, generator, whatever, any device? The output will be like a first order approximation where you have some time constant here. So this is maybe after 4 tau, and if this is tau, So the system will reach to 63.2% of its steady state value. So you expect some delay between the input and the output. This is for physical system in general. Okay, so you take some time, and this time is represented here by the time constant, tau, or T charging. Charging here refers to the steam. When you have a turbine and you pump the steam in, so it takes some time to give you like a mechanical power output. So this is the time constant here of the turbine. Okay? I hope the answer is clear.
Yes, clear, Doctor.
Okay. So let us go move forward and see what is the delta P valve, how to control the governor, how to control, sorry, the steam valve here through the governor. So let us see the governor. So this is the governor. This is the governor. It is a controller, very simple controller. This integrator is simply an S domain is 1 over S. So you can have here an integrator. And you have some, of course, gain here, kg of the governor, the gain of the governor. What is the function of the governor? Governor, it measures the speed, as we mentioned earlier, and you compare the speed with the reference speed, which is 2 by f, and the reference frequency is 60 hertz. So omega reference here is 377 radian per second. So you measure the speed. This is the actual or measured, and this is the reference. If you have an error, this error will go through this controller, and at the end you have the output of the controller here to adjust the steam valve opening. You allow more steam. If you have here the speed is going down, then you need the steam, more steam to go through the mechanical to the turbine in order to increase the mechanical power, and vice versa. If you have overspeed, then you need to close bit the steam valve in order to reduce the mechanical power through the turbine. Okay, so this is the governor. This is called the speed regulation, and we will discuss it in few moments. This is the load reference set point where you need the frequency to be 60 hertz. So if you say, مثلا, for example, this generation power station, or this power station, we need 50 megawatt output of this. So in this case, you adjust this to 50, so you can get 60 hertz corresponding to the output here of this. Okay. So again, if you need more power and you increase this power to, for example, 70, if you load more, in this case the frequency will be lower. So you have to adjust this one in order to increase the frequency to be 60 hertz again to at 70 megawatt and so on. So this is the load reference set point. We will talk about it in few moments later on. So so this is the governor structure, and as you can see here, it is just feed forward gain and integrator here, and you have here like a feedback R, and based on your experience in block diagram reduction, you can reduce this block diagram by moving this R from here to both signals there. So you multiply here by R and you divide here by R, 1 over R. So you can have it like a unity feedback, and then you can reduce it. This is J. Now G is feed forward is kg times R over S. and the feedback is 1. So you can reduce this as G over 1 plus GH. So you can end up with this figure. This is the case, and this is the reduction. And eventually, when you take 1 over kg R as a time constant, we call it governor time constant. This factor is 1 over kg R. We set it as governor time constant. So we end up with the governor representation as such. So this is a delta V valve, the output of the governor, and this is the governor representation, first order system, and this is the load reference set point, and this is delta omega. Comes from here, which is omega reference minus omega, or actual omega. Yeah. So you can, of course, connect this block diagram to the previous block diagram here. Now we have delta B valve as output, and we have a feedback from delta omega. So we can combine this block diagram with that one. So you have this, and this comes from delta omega. So you can take from delta omega here after the generator back to this one. So this is the block diagram. Let us assume we'll go back to this one now, but this is now the block diagram of the generator, the block diagram of the turbine, the block diagram of the governor, and this is the feedback from delta omega. So you have delta omega multiplied by 1 over R, the speed regulation. R is the speed regulation, and it comes here to the load reference set point. So this is the governor and the generator and turbine representation. Now, let us talk about R. R is a speed regulation, and this speed regulation, if you look at it carefully, this R equal to delta omega if delta B equal to 1 per unit. Yani if you change the output power, you change the output power of the generation plant from 0 to rated, yani 100% rating, delta B equal to 1 per unit. So from 0 to 1 per unit, this is the change in delta omega. When we say R equal to 3%, for example, if we are equal to 3%, that means the null frequency will change, or the speed will change by 3% if we have, 100% change, or delta B equal to 1 per unit. So, for instance, 3% regulation of a unit indicates that 100% or 1 per unit change in the output power requires a 3% change in frequency. So this is very famous characteristic, which is called the droop characteristic. This is the frequency versus the output power here. So if there is no output power, if the system running at no load, so this would be the frequency. If you start loading the system, then the frequency starts decreasing. If we say no, the speed regulation at 3%, that means at 100% here, you will find out the frequency will change by 3%. And if this is 60 hertz, if you adjust your network, your system 60 hertz at no load, so with this 3%, so how much the frequency would be here? 3 times 3 over 100, so 3 over 100 يبقى 18 يبقى 0.1 ولا 1.8. 60 multiplied by 3 over 100, so it is 1.8. So if you start here with 60 hertz at 0 power, you will end up with 58.2 hertz at B equal to 1 per unit. So this is the physical meaning of the speed regulation. Speed regulation gives you an indication of how much the frequency will change if you change the power output of the system. And definitely R is the slope of this. R is the slope of this characteristic, of droop characteristic. So this is delta omega or delta F over delta B. If this is delta B and this is delta F, so delta F over delta B or delta omega over delta B. Okay, so the R is a slope of this characteristic, and this is very natural characteristic. And if you increase the power, then the frequency will change definitely. What makes the frequency back to 60 hertz is the governor control, and we also need some supplementary control later on, as we will discuss in a few minutes, inshallah. So this is the physical meaning of the speed regulation. It gives you how much the frequency will change by changing the output power of the system. So this is the complex is to set R on each generating unit so that the change between 100% result in the same frequency change for each unit. And if you have several units are running in parallel, so this R, you have R1, you have R2, you have R3, you have different characteristic here and there. This is for generator 1, and this is for the generation plant 2. You can have, if you have like this R, and this is the power. If you have just a straight line here, what does it mean, this is straight line? This is the group characteristic. What does it mean? How much R here?
Zero.
Zero. That means in the frequency is constant. Okay, delta omega is zero. Whatever the power taken from the generation plant, its frequency is constant. But yes, this could be theoretical, but usually we have like droop characteristic. Frequency will drop as the power increases, the power output increases. So this is the speed regulation. Okay, this is just illustrative example. If you have two different machines and each machine has its own drop characteristics. So this is R1 and this is R2. And if you have any change in the power output or the demand, if you increase the electrical power output, how to distribute the change in the power? Your load is 100 megawatt, and you distribute it by economic dispatch problem. You solve this among two generators. Generator 1 will take 30, and generator 2 will take 70 megawatt. So this is the economic dispatch solution for this load, BL. Okay? Is it clear? Right now, if BL becomes 150 megawatt, how this 50 megawatt will distribute it among these two generators? So what is the new output here, and what is the new output here? This is the situation. If this is R1 for the generator number 1 and this is R2 for generator number 2, So this is the first, or this is the initial operating point. This is the initial operating point. طبعا keep in your mind انه if these generators are running in parallel, يبقى we have the same frequency. So if they are running together, we have the same frequency. So this is F0, the initial frequency. And if we have like 150 megawatt or 50 megawatt increase, in this case, definitely the frequency will decrease. And at a certain frequency, which is equal on both sides, on both generators. So this is the new operating points. And you can see how much delta B2 and how much delta from generator 1 to be added here. So this is B1 prime and this is B2 prime, the new power output, and this is the new power output. Delta B1, this is delta B1, plus delta B2 gives you equal to the difference in the power. So you can also mention, or you can also say that this speed regulation factor here will also govern the distribution of the excessive load among the running generators. So you can see here delta B1 and delta B2. So this is the impact of the speed regulation on the performance of the generation plant. Do you have any question? Okay. So assume that when we start with this 60 hertz here, and this is the drop characteristic. Can we change the drop characteristic? Can we, not changing the drop characteristic, can we push it up? Can we push it up in order to do what? In order to keep the frequency constant at 60 hertz, whether the generator running at no load, whether it provides 50%, whether it provides the full capacity, or even in between. Yani you can have here at 30%, you have another same or parallel characteristic. So can we play with this characteristic ups and downs in order to keep the frequency equal to 60 hertz, whatever the power output of the generation plant? This can be done by changing the load reference setting. So you can adjust the load reference setting here in order to push this characteristics ups and downs in order to keep the frequency equal to 60 hertz, whether the generator plant operates at no load or 30% or 50% or full load. So you can make this load reference adaptive in order to fix the frequency. By changing the load reference, the drop characteristic can be set to give reference frequency at any desired unit output. So I don't know. Okay. So by adjusting, if you have any question, please ask. By adjusting this set point on each, raise your hand and I will pick your question. By adjusting this set point on each unit, a desired unit dispatch can be maintained while holding the system frequency close to the desired nominal value. And this is the boundary between response capability and economic allocation by economic dispatch solutions. So again, this is the same characteristic. You can push this characteristic up. You have here the speed equal to 1 at 0.625. This is the operating point. The frequency is our speed is unity. معناها ان هي الريتد سبيد، معناها ان الفريكونسي here is 60 hertz. So you can move this characteristic up in order to have again 60 hertz at full load. So this will be done through the load reference set point. So this is a load reference set point as we have it here. This will make sure the frequency will be 60 hertz whatever the loading of the system. So this is the block diagram of the whole system, except if we have any connection to the neighboring utilities or neighboring countries. So this will be also reflected here, as we will see in a few minutes. But this is the governor, this is the prime mover turbine, and this is the generator, this is the load, and the output here is the mechanical power, and this is the valve, and this is the load reference, and this is the speed regulation here feedback. So this is the block diagram. Right, let me ask you now, if this is the block diagram, can we derive the transfer function, for example, from delta omega of S over delta, let us say BL of S? Assume that this is a disturbance, this is the input, we will make a step change in the load, and we need to study the response of omega, response of the frequency. How much of the steady state error in the frequency? And of course, if we go deeply in dynamics, we can also design, or we can also see in the frequency will change until it goes back to its steady state value. So we are not interested in, at least in this course, with the dynamics. Here, we need to see what is the impact on the steady state value of the speed. So can we derive this transfer function based on this simple block diagram?
Yes, we can use the signal flow graph.
What is G? What is H? And we can see the transfer function is G over 1 plus GH. So what is G, يا شباب? We need the transfer function between delta omega and delta BL.
G is 1 over ms plus d times 1 over r.
This is the output, by the way. This is the input, and this is the output. So what is G? This is G. What is H? What is the feedback? From delta omega.
1 over R plus.
Up to this point. So 1 over R multiplied by 1 over plus STG multiplied by 1 plus STCH. This is the feedback. This is represent the feedback. Okay. خلي بالكم ان هنا we can assume two inputs, delta BL and the load reference. Let us say delta B reference here. So when we want to, this is for linear systems, when you want to design or when you want to derive the block diagram or the transfer function between delta omega and one of the inputs, you kill the others. And this is deactivated. Yani this is zero. Okay. So this loop will represent a feedback. This is the input and this is the output. Okay. Is it clear? Of course, we can also derive a transfer function between delta omega of S and the delta B reference. In this case, what is G? This is the input now, and this is the output. What is G? three blocks are multiplied together. This is G, and the feedback is 1 over R. So this is for that transfer function. Okay, of course, you can combine if you want to have delta omega of S as a function of the two inputs. So you can apply superposition theorem as far as this is a linear system. Superposition can be implemented, and you can add these two transfer functions together. So, but anyway, in our study here, we are studying the impact of the change in the load on the frequency. As I mentioned earlier, in this problem, automatic generation control is, earlier it was called the load frequency problem, load frequency control. So how much the impact of changing in the load on the frequency. So this is our input now, and this is our output. So this is G, this is the feed forward transfer function, and this is the feedback from the output back all the way until we have this input here. So all this would be like a feedback here. So we can implement again G over 1 plus GH, and we can derive the full transfer function. Type, okay. We will come back to transfer function later on. Using the block diagram, find the frequency change delta omega for a stable change. It is here. Yeah. So this is an example. We need to derive the transfer function between delta omega and delta BL. And if delta BL is a stable change, and a stable change, and delta BL of S equal to what?
Unit.
Delta BL over S, if it is a stable change. Okay? Is it clear? And if we have
Yes.
5% increase, so this becomes 0.05 over S. So this is the stable change in delta BL. So as we mentioned, you can get the transfer function. So this is the G over 1 plus GH, and this is all this H, the three blocks here, 1 over R multiplied by this, multiplied by this. And of course, you can see the sign here. This sign comes from being, this input is negative here. So this minus 1 will be multiplied by this G. So this is G, and this is 1 over. And keep also in your mind, this one, we have here a minus sign. So this minus sign will be like a negative feedback. So it is not a positive feedback. It is a negative feedback if you multiply this sign by this sign. So 1 plus GH. Okay. So if you want to get the steady state value, so you get the limit here, or the limit of S delta omega of S as S goes to 0. This is the steady state in in S domain. It is similar to as T goes to infinity in time domain. So delta omega steady state equal to limit. Of course, you can multiply, and you have delta BL now is 1 over delta BL over S. So at the end, you can just substitute S equal to 0. So you end up with this figure or this value. That means if we have a steady change in load, the frequency will have a steady state error equal to this. So minus delta BL over 1 over R plus the D factor. So note that if D equal to 0, the change in speed would simply be equal to delta omega equal to minus R times delta BL. So this is exactly the physical meaning of R, and that gives you the change in speed if we have unity change in output power. So this is the steady state error. If you have different generators running in parallel, so you can have 1 over R1, 1 over R2, 1 over Rn. And you can say that this is 1 over R equivalent, and 1 over R equivalent equal to one summation of 1 over R. It is similar like we have in resistors connected in parallel. So this would be if we have more than one generation plants running in parallel, so we can have this value. Okay, so is it clear? Do you have any question? So the remaining is if we have interconnection between the generation plant and neighboring utilities or neighboring countries, how to represent the interconnection link in this context of the automatic generation control. The power flow through the tie line, as you know, assuming that this is a DC load flow, the power equal to 1 over X times theta 1 minus theta 2. This is the power between utility 1 and utility 2. This is the G1, and this is generation plants or countries, utilities, whatever. So this is theta 1, and this is theta 2, and this is B12, and this is X12, which is the reactance of this transmission line. So 1 over X tie multiplied by theta 1 minus theta 2. So the change, the incremental change of delta B equal to the incremental change in the angles 1 over X. So 1X is constant fixed. So in order to convert this angle to delta omega, which is of our block diagram, we have delta omega. So we can express the angle by delta omega. So you need an integrator. So 1 over S here. And when you have this, you also multiply, then this becomes embryonic. And this is in radian. So you have to multiply here by omega 0, or the rated speed in radian per second, which is 377, and here 2 pi times 60. So this omega equal to 377. This is the base value of the speed. This is the base value of the speed. So the speed here is embryonic. In order to get it in radian, to convert between the angle and the speed embryonic, so you have to take the base value of the speed into consideration. So we have this T, and this T equal to omega base multiplied by 1 over X tie, which is here. So 377 for 60 hertz over the reactance of the tie line. So this is delta B, or the change in the power flow through the interconnection link between the utilities, equal to delta omega 1 minus delta omega 2. So if you have two plants, this is Saudi Arabia, and this is other countries, ولكن مثلا whatever, Egypt or GCC, and this is the tie line in between. So the power in the tie line, assume that the power, as we mentioned, it's B12, معناها انه goes from the area 1 to area 2. So this power will represent, for the area 1 will represent load, and for the area 2 it represents a generation. So this is positive, and also the mechanical power is positive. And this power in the tie line represent here as a load. This load is negative as well, and they represent in the second area, it represents a generation, so it becomes a positive here. and this is the delta B tie, which is equal to delta omega 1 minus delta omega 2 multiplied by T times T over S. So this is the representation of this equation. Delta omega 1 minus delta omega 2 multiplied by this gives you delta B tie, and delta B tie is a load here in this generation, in this area, and generation in the other area. So this is the block diagram of the two-area system. This is two-area system. You can say eastern operating area of Saudi Electricity Company and central operating area of Saudi Electricity Company. So this is the tie lines, the representation in this. Is it clear? No question, either you are fully understand or I'm not fully clear.
اللي هو النيجاتيف اللي فوق لان اللي هو الاريا الاولى هي تسوي كانما تسوي اللي هو تودي الباور للاريا الثانيه.
Yes, you are right. I'm saying هنا B12 from area 1 and this is area 2. This B12 represent for the area 1 load ولا generation? Load ولا B mechanical? Load ولا generation? This, if you export 100 megawatt from your area to the neighboring area, يبقى ال 100 megawatt دول يمثلوا load بالنسبة لك ولا generation؟
load.
يمثلوا load. And for the other area represent a generation. So this is the positive here and negative here. Okay, this is the and why this delta B tie is added here and subtracted here. It's subtracted from here, then this is load, and the delta B tie here or B tie here represent a load, and then the other area represent a generator or a generation power. Is it clear?
Yes.
Any other question?
ممكن تعيدها دكتور؟ ما فهمتها كويس.
طيب احنا بنقول هنا انه this is the representation of the tie line model. I hope انه up to this figure everything is clear. I hope. If you have any question, please ask so we can move forward. This is the generator modeling. This is the turbine modeling. This is the governor modeling. And this is the feedback as we discussed for the governor. And this R is speed regulation, and we discuss the physical meaning of this. And this is the transfer function between delta omega and the delta BL. As we mentioned, this is represented G multiplied by minus sign here, and all this represented the feedback up to the input. So this is the input here. So this is represent the feedback. So you can easily get the transfer function G over 1 plus GH. And since this is a linear system, we can use the superposition. So if we need the transfer function with this one, we kill this one or deactivate it, and then we can proceed. So this gives you the steady state error and the speed if we have a stable change in power, and if we have more generators running in parallel. So this 1 over R will be 1 over R1 for the area 1, area 2, area 3, and so on. For the tie line representation, if you have two areas are connected together, from the DC power flow, and the power through this transmission line equal to 1 over X, theta 1 minus theta 2. So can we get the incremental change? If we have incremental change in in angles, and then becomes delta B, the incremental change in delta B equal to 1 over x. طبعا x is constant fixed. This is the reactance of the link here, multiplied by delta theta 1 minus delta theta 2. So we have, in this block diagram, we have delta omega. So we need to express delta theta by delta omega. Otherwise, if you don't, then we need to add here, this is delta omega. If you integrate it, then you have here an integrator to get delta theta if you want. So you have an integrator of delta omega to get delta theta. We don't want to complicate this block diagram. We will keep it as delta omega of our output. This omega is just linked to the frequency right away. So we need to replace delta theta 1 by delta omega 1. And omega is is what? Omega is the integrator of theta, right? Sorry, derivative of theta, d by dt. So of theta, okay? So this is s theta, or theta is equal to omega over s. So you replace delta theta by omega over s, delta theta 2 by omega 2 over s. And since this speed is expressed in per unit, so we need to multiply this by the base speed. The base speed is, which is 377. So this t equal to 377 over x. Okay, so over multiplied by 1 over x. So to represent this equation in the block diagram, طبعا احنا we're talking about tie. So we have two areas, we have two utilities connected together. So this is the utility 1. So this is the area 1, let us say. And this is the area 2. And this is the link, the tie line. Delta B tie, as we derived it, equal to T over S multiplied by delta omega 1 minus delta omega 2. So you have here delta omega 1 minus delta omega 2 multiplied by Ts. This is delta B tie. The delta B tie for the area 1, if this is the direction, for the area 1, the power here represents a load. For the area 2, this power represents a generation. So we add here a negative sign, delta B tie, a negative sign here, and this represents a load. And in the other area, we add it as with positive sign, and this delta B tie represents a generation for the area number 2. So this is minus sign here and the positive sign here. So this is the representation of delta B tie. I hope I addressed your question. Right, okay. For a load change delta B1 in area 1, steady state frequency after all oscillations have dampened out, and transient period, after the transient period passed away, will be constant and equal to the same. طبعا of course, keep in your mind that if we have this system, we have the same frequency in the whole system. يعني frequency here, if it is 59.5, also the frequency here also will be 59.5. and the frequency will be the same at steady state. طبعا ممكن يحصل change في frequency, but this is during the transient. يعني انت you can say انه if we plot the transient period, this would be the frequency 1 of the area 1, and this could be the frequency of the area 2. But at the end, at steady state, they will merge together and F1 equal to F2 at steady state. Now at transient, they are oscillating against each other, so you have different frequencies. The frequency is moving up, the other area, the frequency is moving down. But at steady state, you have the same frequency. Okay, so at steady state, we have delta omega 1 equal to delta omega 2 equal to delta omega. And the B mechanical 1 minus B tie minus delta B equal to delta omega D. This comes from the block diagram. From this block diagram, if you have a steady state, يعني الاس بكام؟ الاس بكام؟ at steady state. How much the S if you need to get the steady state؟ الناس كلها left the class ولا ايه؟
Is it one?
موجودين.
طب كام الاس at steady state؟ At steady state, if you need to find the steady state value,
Zero.
يبقى الاس بزيرو. In time domain, steady state, يبقى T approaches infinity. طيب تمام. At steady state, if you look here at this summing point, if this is a steady state and no transient, this is equal to 0 now. So you have delta B mechanical 1 delta B mechanical 1 طيب يمكن معترض على الميكانيكال، خليها مثلا ماينس دلتا بي ال ماينس دلتا بي تاي. شكله معترض على الميكانيكال. الميكانيكال دايما عامل لنا مشاكل في كل حاجه. طيب وفعلا معترض على الميكانيكال. اوكي. This is equal to the output power here, or this power will be multiplied, or this input, total input here will be multiplied by 1 over d1 to get delta omega 1. So this is at steady state. احنا خلاص ان الاس here at steady state, this s goes to 0. So 1 over d1, b mechanical minus pl minus b tie multiplied by 1 over d gives you delta omega. So delta b mechanical minus delta bl minus delta b tie equal to d1 times delta omega 1. And also you can repeat this here. You can repeat this one here. So you have here delta b mechanical minus delta bl2 plus b tie multiplied by 1 over d2 equal to delta omega 2. If you have a change in area 1 only, in load of the area 1, if this is equal to a certain value, 5% or 10%, but there is no change in the area 2. If there is no change in area 2, يبقى delta BL2 equal to what? Equal to 0. So this is the here. If we have only change in delta BL1 in area 1, so this is B mechanical minus delta B minus delta B1 equal to this one, and B mechanical 2 plus delta B2 and DBL2 equal to 0, since there is no change in the power in the load in area 2 equal to this. So of course you can say in the delta B mechanical 1 we can express it as minus delta omega over R1 and the delta mechanical 2 equal to this. Again we mentioned انه R equal to delta omega minus over delta B, and as far as the slope is negative, as you can see from the characteristic, you can express it as such, or you can come to the block diagram and you can derive it also. If you have here a steady state, this S will becomes a 0, but this is 1. At steady state, this also the gain here becomes 1. So you have here in the delta B mechanical equal to what? Equal to delta omega multiplied by 1 over R multiplied by the minus sign. So you can have delta B mechanical at a steady state. Look, now we are emphasizing in this value at a steady state. This part equal to 0 and this part equal to 0 at steady state. S goes to 0. So delta B mechanical at steady state equal to minus 1 over R multiplied by delta omega. So you can express this here in these two equations. Delta B mechanical equal to minus delta omega over R1 and minus delta omega over R2. طبعا as we mentioned انه at steady state delta omega 1 equal to delta omega 2 equal to delta omega, same frequency in both areas. And of course you can solve these two equations together and you can find how much delta omega will change in the speed or in the frequency with the step change in delta B, and also how much the tie line change if you have a change in the load power in area 1. Of course, this can be repeated for area 2. For area 2, delta B equal to 0, and you have delta BL2, and you can repeat this, derivation. It's quite easy. Is it clear? This is the steady state error in the speed. If we have a stable change in, in area 1, in the load of the area 1, and this is the steady state error, or change in the tie line power, if we have loaded change in area 1. Okay. طيب, without governor, if there is no governor, we cannot change the mechanical power. If there is no governor, without governor, B mechanical 1 equal to 0, delta B mechanical 2 equal to 0. There is no governor, we cannot change the steam. So in this case, same equations as before. If we have a change in area 1, and these are the two equations that we derived earlier based on a steady state condition. Here we will not express delta omega as delta omega over R. No, there is no governor here, so this becomes 0 and this becomes 0. So you can get delta omega as a function of delta B1 and delta B tie as a function of delta B1. So you can solve these two equations having delta mechanical equal to 0. So you end up with this change in. طيب, let me ask you, if you compare this, what do you think? Having a governor will improve the frequency response, or without governor, we will have better frequency response. This is the steady state error for the governor. If we have a governor, without governor, this will be minus delta BL1 over D1 plus D2. So this is delta omega steady state without governor. What do you think if you compare these two formula together? Is it better to have a governor or not? Whether the governor will improve the frequency response or not?
I think the governor.
Yes.
Of course, this R is very small. This could be 0.03. So 1 over 0.03, so it becomes, so you have a speed regulation, so you can push the frequency towards 60 hertz if you have a governor. If you can control the steam, you can increase the mechanical power and you can increase the speed, or you can do the opposite if the speed is high. So mathematically also from here you can see, you know, if this is 0.03 per unit, so this becomes 33, and this also becomes like 33. So you increase the denominator here much with this speed regulation factors. So this delta omega will be much less than that we have here without governor. That means in the steady state error, the change in the speed will be much less with the governor. طبعا governor plays a very important role in automatic generation control or load frequency control. So this is the without governor. And we can have an example. Last example. You are given two system area connected by tie line with the characteristics shown in the table below. This is area 1, the speed regulation. This is the D damping factor, or the the gain of the frequency dependent load, whatever. This is given before, defined before, and the base megavolt ampere is 500. R for the second area R2 D2, and the base is 500 megawatt. Fortunately, the base value equal to each other. Otherwise, we have to modify the solution. We will see later. If this is different, خلينا نقول على طول هنا, if we have S new, S base new, if we have different, we have to unify the bases. So R will be adjusted, R old multiplied by S new over S old. So this is the so this is how to adjust the speed regulation if we have different bases. If we have different bases, let us select a new base, and then you adjust this 1.01 per unit by multiplying the old value times S new over S old. And also for R2, you will do the same unless you take one of the bases as your new base. So you have to adjust this if it is allowed. The change of 100 megawatt occurs in area 1. So you have delta BL1 equal to 100 megawatt. If you take 500 megavolt ampere base, so this 100 megawatt is 0.2 per unit. 100 over 500, so it is 0.2 per unit, delta BL. What is the new steady state frequency? And what is the change in the tie line? We need delta F steady state and the delta B tie at steady state. And we derived already the expressions before. Assume both areas were at nominal frequency 60 hertz to begin. So this is the initial frequency 60 hertz. So how much the final frequency and how much the tie line steady state value of the tie line. If we have 100 megawatt change in the load of the area 1. So I don't think this is the just substitution in this. You have here delta omega equal to minus 0.2 over 1 over R1, 1 over R2, D1, D2, and this is the change in the tie line. And even if you don't consider the governor, so this would be the change in the speed, and this would be change in this. So yeah, just substitute. Of course, I'm not asking you to remember this or to memorize these expressions, but if you have the block diagram in your mind, which I think it's more difficult than memorizing this expression. Anyway, so you can just substitute to get the delta omega at steady state. Keep in your mind this is in per unit. So if you have frequency, you multiply by the base frequency 60 hertz, and 60 minus the change multiplied by the base, so gives you this is the F new. This is the new frequency, and delta B tie we also multiply by this, so it comes to minus 33.6 megawatt. So this is delta B tie, يعني tie line power will be, you know, reduced by 33.6 megawatt. Okay. The change in prime mover power would be delta B mechanical minus delta omega over R1, delta B mechanical 2. This is in per unit, and you multiply by 500 to get it in megawatt. 500 to get it in megawatt. And this is the change in mechanical power if you want. And the total changes in generation is, you can see, you can add these two B mechanical together. And then you have this is the change in generation and load. You know, the load is 100 megawatt change, and what we can generate is 98.1. So we still have a deficit between the generation and the load, and this is why the steady state frequency not reaching 60 hertz again, but it is slightly below 60 hertz due to this deficit between the generation and the load. Load changes by 100 megawatt, and while the change in the generation is 98. So we have some deficit shortage, and this is why the frequency is slightly dropped behind this 60 hertz. For area 1, you can say, no, this is the deficit in area 1, and this is the deficit in area 2. Okay, so in order to cover this deficit between the generation and the load, and the push the frequency back to 60 hertz, we need some kind of additional or supplementary control here. This is the load reference point. We need to control this load reference point again by like an integrator or BID controller can be used. In literature, you can have BI or BID or just I integral controller. So you can have the frequency again back with this controller to adjust the load frequency or the load reference set. In this case, you can push the frequency back to 60 hertz and compensate for the very slow power. طبعا definitely you have some rules. If you have, do you have a question? I saw one hand.
When you found the frequency, why didn't you divide by 2 bar?
This is, yes, you have here, this is the per unit, right? البير يونت frequency هو نفسه البير يونت speed، يعني they are equal in per unit، لأنه البيز frequency equal to 60 هرتز، البيز أوميجا equal to 2 by f، so it is 377 radian per second. Okay, so m per unit, the frequency equal to the speed, m per unit. Okay, so this is why you can do the following. If you are not convinced with this, you can do the following. You can have the speed. Let us find the speed. So this, you multiply this by 377, right? To get the speed in radian. This is delta omega multiplied by this. And then you divide by 2 pi in order to get the frequency. So the 2 pi embedded here will go with the 2 pi embedded here. So you can have per unit quantities multiplied by directly 60 hertz. Okay? Any other question? A rule of thumb, definitely, this is the rule of thumb. If you have increasing in load of area, yes, time is over. Time is over, right? Time is over. So, okay, let us, probably this is the last slide. if you give me just a few seconds to finish in order to close this subject. Delta BL1, if you increase the load in area 1, you need to increase the generation in area 1 in order to keep the beta constant. If you have decrease of the load in area 1, you need also to decrease the power generation of area 1. If you increase the load in area 2, you increase the generation of area 2. If you decrease the load in area 2, you decrease the generation in area 2. This is why, to keep beta constant, we need to respect our contracts with the neighboring contracts. Okay, this is enough. So if you have any question, stay. If you don't have any question, then you can leave. And yes.
Regarding the project, can you please postpone the submission?
When the submission?